Welcome to the second video for the lab on torsion and bending of a circular hollow tube. In this one, we'll look at the sources of stress for our points that we're considering. When we're working with this loading, we're going to have both torsion from this eccentricity, and we're going to have bending moment from the load being out here. So we're going to have a lever arm in both this direction, and we're going to have a lever arm in this direction. So we'll have both torsion and bending moment. So our stress state, we will have some normal stress from bending moment, and that's going to of course be equal to the moment times our distance from the neutral axis divided by our second moment of inertia. Now, in this case, we know what the moment is going to be at the top, because we have the location of our strain gauges known. It's 6 inches from there. So our value for our internal moment is going to be 18 inches minus 6 inches is 12 inches times the load P. So we know that M will be equal to 12 inches, not the full 18 inches, because our strain gauge is not at the boundary condition. It's going to be 18 inches times whatever our load P is. And we're going to have Y be equal to the outer radius of our pipe. Alright, so we're given the dimensions of the pipe here, so you can just go ahead and use those. Remember that it's the radius, not the diameter. And the second moment of inertia should be pretty easy to find for a hollow pipe. It's going to be equal to pi over 4 times the outer radius to the fourth minus the inner radius also to the fourth. So that's what we'll be using for our bending moment normal stress in the x direction. We're also we would have shear stress for this, right? We would have shear stress from the lateral load. And shear stress is going to be equal to the shear force, which would be P in this case, times Q over I, and the thickness. But in this case, okay, sure, V is equal to P, fine, but Q will be 0, because we're looking at the top, and this drawing is not great, but it's located on the top of our cross section, so Q will be 0. So we don't have to worry about shear stresses due to the shear. We do have to worry, however, about shear stresses due to torsion. Right. So that is going to be equal to the torque applied times the outer radius, or C, which in this case is going to be the outer radius, divided by J, our polar moment of inertia. So that's going to be the shear stress that we have to worry about. Remember, that is pure shear, but it's not going to induce any normal stresses. So the only normal stresses we have to worry about are due to bending. The only shear stress we need to worry about at this point on top or bottom is going to be due to torsion. Alright, the next video will be on using principal stresses and, well, Moore's circle to obtain the principal stresses from these. It should be a whole lot of fun.